Afternoon, everyone. So there's the folders going round so you can submit your work. Yeah, I've had quite a few questions, so I assume that it was not as easy as I assumed. But hopefully it will help you fixing some ideas. Remember, if you have questions, you can always come to office hours. Wednesdays, have 1 to have 3. If you cannot come to office hours, drop me an email and we can make an appointment and speak about these things and you can ask questions. But in any case, probably now it's too late, but submit work, because even if it's not perfect, it counts towards your final mark. So I think it's advisable to do that. Okay. So what we are going to do today, I'm going to try and finish talking through MCMC, definitely in general, and hopefully I will get to Gibbs sampling, which is the technique that we will be using in the following weeks to do inference, to carry out Bayesian inference in the examples in the next chapter. Okay. So just a quick reminder of where we stopped yesterday. We're trying to set up the Metropolis-Hastings algorithm. Okay, and this algorithm is useful to generate samples from a probability distribution. In this case, in this notation, that is f of x. X is the random quantity. That we cannot sample directly from, okay? So what we're doing is we're using a proposal density to generate a Markov chain that will eventually converge to that distribution, okay? And the transition kernel, so the mathematical tool that allows us to go from one state of the chain to the next, is defined by the Metropolis ratio, which is the ratio of the target density evaluated at the proposal distribution and the target density at the current state of the chain, and then the proposal distribution evaluated at the current divided by that same distribution evaluated at, sorry, that there's a typo there. That should be xt plus 1. Hopefully that is okay in your notes. If not, I will make sure that it is. So just please make a note. This should be xt plus 1. Oh, sorry. No, it's fine. Sorry. Y is xt plus 1. Sorry. It's fine. It's absolutely fine. It's cool. Sorry about that, panicking. And then this is the transition kernel, but the transition kernel allows us to either accept the proposed value or reject it with some probability, okay? It's not deterministic, it's probabilistic. And that probability is the mean of 1 and the Metropolis ratio. And this is the actual mathematical tool that makes sure that if we generate this Markov chain in this way, after some number of repetitions, we will be sampling from the target distribution. Again, it won't be a random sample, it will be a correlated sample, but a sample from the target nonetheless. Okay? So, if you notice here, we're talking about a target density, okay? And that is the role that our posterior distribution will have. So if we just, I just say something about specific choices of proposals before plugging in the posterior. It's frequent to use a symmetric distribution as a proposal. If you remember on Tuesday, we were using a Gaussian distribution to propose values to sample from this Cauchy, and a Gaussian distribution with the mean at the current state of the chain. So we will propose a value from that distribution. So when we evaluate that density in the proposed value, or evaluate that density at the current state of the chain given the proposed value, that Gaussian is symmetric, so we're changing the mean for the proposed value and the proposed value for the mean. So the actual value of that density is the same. So when we plug that back into this ratio, this function has the same value, so it cancels out, and we end up with the probability of accepting the proposed value equals to the mean of 1, and then just the ratio of the target at the proposed and the current state of the chain. So what that means basically is that this makes the evaluation of the functions in R, in this case, a bit more fast, right? A bit faster. And we already said that under certain regularity conditions of this proposal, and that basically means that that proposal distribution, the support of that distribution needs to cover the support of F, of the target. Then we will eventually be sampling from that target distribution, okay? Regardless of the choice of the proposal and the starting value, okay? So that is really powerful, because then we can, for any distribution that we can think of, we can generate samples from it by using simple known distributions, okay? So if we go back to our problem, if we want to do MCMC for posterior distributions, that will be the probability in the metropolis scheme. But now we have a problem, because obviously we're trying to do this because we don't know the posterior distribution, right? That is the problem. We don't know the proportionality constant. However, if you look at that ratio is the product of the prior times the likelihood divided by the normalizing constant. And the normalizing constant is a function of x only. And in this case, x is not changing, so it will cancel out, okay? What that means is that we don't need to know the normalizing constant in order to implement MCMC for Bayesian analysis. And that's the reason why MCMC is used heavily in practical Bayesian statistics. Okay. So again, you have this in your notes, and you have a sketch at least of the proof of why using this transition kernel you will end up sampling from the target distribution. That is beyond the scope of the course. That won't be in the exam. It's just for you to have an idea of how this works. Okay? What is important to us is how to implement this scheme. So the first thing we need to think about is how to choose a proposal density. We know that if the proposal density is symmetric, then it will make our calculations a bit easier. So that is one rule of thumb. It needs not to be symmetric, but if it is, it will make life easier. Then we need a starting value. And with those two elements, then we can just crank the MCMC, and it will produce samples from this Markov chain. We will run that algorithm a long number of times until by some time t, we have some idea or some notion that this Markov chain has converged to a stable distribution. And we will use all the observations after that time to equilibrium to make inference. Okay. There are some details that we that have to be discussed here, but I think we've talked about them on Tuesday, and we will be talking about them again in the next two practical sessions. Okay. One thing is how to decide when the chain has converged, and again we basically look at the traces of the chain and look for evidence that the traces are stable and hovering around a central value with no discernible pattern. That would be some graphical checks for convergence. How to choose the starting value. This normally is not a big problem. It will make the sampler to converge quickly, and probably you will remember that from Tuesday, and I will show you a picture to rejog your memory in a second. But if we choose this value close to where the bulk of the target distribution is, convergence will be faster. So we'll need to run the sampler for a smaller number of times. And this is a bit more tricky, how to choose a proposal distribution. In principle, we would like to have a proposal distribution that looks like the target. But obviously, in practice, we don't know the shape of the target, so that will be a problem. And what is done in practice usually is to choose simple known distributions that are easy to sample from. Usually Gaussians, if the support of the parameter is the reals, or gammas, if the support of the parameter is bounded in between 0 and infinity, or a beta distribution if the support is bounded in between 0 and 1. Okay? So these kinds of things. So just to show you a little bit of the maths behind what we did on Tuesday, what we wanted to do was to sample from this distribution. This is a Cauchy distribution, which is a T distribution centered at 0 with scale 1 and 1 degree of freedom. Okay? So if you look at your distributions handouts, you will realize that this distribution doesn't have a mean, doesn't have a variance, very fat tails. Okay? We know the distribution, and we could sample from it directly if we wanted to, but the exercise is to show how we can use commonly known distributions to sample from an unknown one. Okay? So that is the kernel of the distribution, 1 plus theta squared to the minus 1, and we will use this Metropolis algorithm to create a Markov chain that has stationary distribution, precisely that one. Okay? So we have f of theta, f of x. That's one thing that we have. We need now a starting point and a proposal distribution. As a proposal distribution, we know that this t, this Cauchy, is defined in minus infinity to infinity. So we need to use a distribution with the same support. A Gaussian is a good choice. We know that the Gaussian is symmetric. It's just written there. That means that the Metropolis ratio will be simplified because this ratio here cancels. So we will have used the ratio of the non-normalized target distribution. And that is that. Okay? In this particular case, we can write the probability of accepting in a bit more easier way to code. And now, if you have the time and look at the actual code that you used on Tuesday, you will see that the for loop or the while loop contains exactly this decision rule. So that is the core, that is the where all the action in the sampler goes in. And the way it works, and that's hopefully what you realized by running the demo, is that we start with a value, a fixed value for the first state of the chain, and then generate a new value from this distribution. We fix P and use the Metropolis ratio to decide whether to keep the proposed value or not to keep it. Okay? So I have here just an example of what we did, but hopefully you will remember what we did. We just proposed a new value, use the ratio, the Metropolis ratio, to decide whether we keep it or not. If we keep it, then the new proposal distribution will be the same Gaussian, but now we center it at the new value. Okay? And we will propose a new value from that one and carry on doing that. And after some time, we will end up with a Markov chain that will be sampling from the Cauchy distribution. Okay? And this is a graph of one of the exercises that we ran on Tuesday. These are chains of length 5,000. 3 of them, one starting at 100, another starting at 0, the third one starting at minus 100. And we can see that if we start the chain near where the bulk of the target distribution is, then it will converge quite quickly. And if we start relatively far away from the center of the mass of this distribution, then depending on how well the chain is mixing, we will have convergence quick or rather slowly. Okay? But in any case, and regardless, at some point, after some point, the chains or the chain will converge, and we can use all those observations, all those realizations of the Markov chain for inference. Okay? And that's how we usually inspect for traces or evidence of convergence. We look at the trace, and once that trace settles and hovers around the central value without any discernible pattern, then we have some evidence of convergence. Okay? All the values of the chain before that point should be discarded, and that is called the burn-in. So we just burn them in. We don't use them for inference, and then we use for inference all the values after convergence. Okay? We can also try and bring down the autocorrelation in the sample. Remember, this is a Markov chain, so there is autocorrelation in the sample, by thinning the chain. That means subsampling after convergence every so often, every second, every third, every fifth, every 10th observation, depending on how strong this autocorrelation is. And the only reason for doing that is to try and have an approximate random sample, right? Sometimes it's very expensive to produce the Markov chains, so dropping values of dropping elements of the chain to try and bring down the autocorrelation is very expensive. So in practice, for complex models, we usually just look for convergence and then keep the whole chain without thinning. Okay. And the other thing that I mentioned on Tuesday is once you have your sample from the stationary distribution, you can use that sample to estimate any characteristic of the target distribution. In particular, you can estimate the whole distribution using a histogram or a smoothed histogram, a kernel density estimator. Or in our case, I think we wanted to estimate the probability of this quantity being in between 0 and 1. Again, we know that distribution, so we can calculate that probability analytically, and that is 0.25. And we did that with a large sample from our Markov chain. And one of the characteristics that I wanted to highlight is that when you have a relatively small sample, the estimates are not very precise and are really variable, but you can make those estimates a bit more precise and less variable by running the chain for a longer time. So again, in practice, if you're able to, the suggestion is to try and run the samplers for as long as possible in order to first achieve convergence, and second, try to make the Monte Carlo error, the estimation error, as small as possible. Okay? Are there any questions so far? Okay. So this is the actual practical strong result for using MCMC, and in particular, we will use one flavor of MCMC that it's called Gibbs sampling, and that's what I will try and explain now. Okay. As we saw yesterday, usually in Bayesian modeling, we have hierarchical models. And even for simple hierarchical models, the dimension of the parameter increases very rapidly. And we end up with posterior distributions that are highly dimensional. Okay? In our two examples yesterday, we had parameter spaces of dimension 12 or so, right? So there are, for very simple cases, we already have large dimensional parameters. So if we wanted to use, we can still use Metropolis Hastings. This is really general. So, and it works for parameters of any dimension. Okay? So we have our on-scale posterior distribution, parameter theta of a large dimension. What we would need if we wanted to run a Metropolis Hastings sampler for this posterior distribution will be a starting point in that dimension, and then a proposal distribution of the same dimension as a parameter. Okay? In our previous two examples, we would need a proposal distribution of dimension 10 or 12. Okay? Which probably are not very easy to come by and definitely not easy to understand and work with. Okay? So what we usually do in practice is to update one parameter at a time. Instead of updating the whole vector of parameters, we take one parameter at a time and do Metropolis Hastings one parameter at a time. Okay? So let's assume that we are at time t, or state t, in our Markov chain. So we have a parameter of dimension d. And what we are going to do is we will go from that state t to state t plus 1 in these steps. So that means that we will update one parameter at a time sequentially. Okay? To do that, I will just introduce some notation. Theta minus I will be the vector parameter vector, without that specific entry, I. And then theta minus I t will be the state of this vector after updating the first I minus 1 components. Okay? So this is just notation. Remember, I'm going to go from theta vector t to theta vector t plus 1 by updating first theta 1, then theta 2, then theta 3. So at the ith step in this updating scheme, theta t minus I will be the vector with the first I minus 1 components already updated, and the rest to update. Okay? So now, given that I am updating one parameter at a time, what I need is a proposal distribution of dimension 1, right? And again, we want the support of this distribution to be the same support of that parameter. Okay? If this parameter in particular lives in minus infinity to infinity, we could use a Gaussian. If it's just larger than 0, we could use a gamma, and so on. Okay? But now, the thing is that this proposal distribution should depend on the whole parameter. But now we have some of these elements that have been updated, some of them have not been updated. Okay? So we need to take that into account. Okay? But it works in the same way. And now, if we want to calculate the metropolis ratio, then we need to evaluate this posterior distribution for the parameter that we are updating, given or fixing the values of the rest of the parameters. Okay, because that we are just updating that parameter. And the decision rule is exactly the same. If this probability is alpha, then we will set the new value to the proposed one with probability alpha, and otherwise we will keep the current state. Okay, so a new name. To these distributions, remember these are the unscaled posterior distribution seen as a function of theta I only, okay? Remember, this notation is important because anything that is to the left of the vertical bar is regarded as random, and anything that is to the right of that vertical bar is regarded as constant, okay? So what we're saying is that the full conditional distribution of theta I is the joint distribution when we regard all the other parameters fixed on the data, and the only random quantity, the only variable, is the parameter that we're trying to update at this time. Okay? I will write an example in the board, so hopefully it will be a bit easier to understand. Okay? And now the real usefulness, well, not the real usefulness, but what makes Gibbs sampling special is that if we are able to identify this function, this full conditional, as a known distribution, then we can sample directly from that one, right? Imagine that we look at this function just as a function of theta I, and this looks like a Gaussian distribution with some mean and some variance. So we could use a Gaussian to propose from that distribution, right? And if we do that and plug this back into the metropolis ratio, everything cancels and we have acceptance probability 1. So that means that if we can sample directly from the full conditionals, we will need not to calculate acceptance probabilities because we will always be accepting the proposed value. And that is Gibbs sampling. Okay? So I know this sounds absolutely awful, but hopefully an example will make things a bit clear. Remember yesterday that we were talking at the very beginning about having Gaussian data, and instead of having a conjugate prior, we had a prior that was a product of a normal and a gamma, right? If you can look at that example, that was the prior structure that we used. We also were able to derive the unscaled posterior, and that was proportional to the likelihood. and the priors, right? Remember that? And I tried to show that if you wanted to find the normalizing constant with this prior structure, you couldn't do that analytically, right? So we're in this kind of problem. We have now a distribution, a posterior distribution in a parameter of dimension 2, and we will need to set up a sampler, a metropolis sampler for this distribution, right? One option that would be probably useful would be to use a normal gamma proposal, because we know that the normal gamma has support in minus infinity to infinity times r positive, which is the support of that posterior distribution, and then use directly metropolis Hastings with that. Okay, we could do that. But we can also try and do Gibbs, okay? So if we want to do Gibbs, we need to find the full conditionals, okay? So the full conditional is this function, this big function there, saying as a function of each parameter at a time, okay? And that means looking at that function and then trying to get rid of any factors not involving mu. So I can drop the last prior, and I need to keep Can you all see that? Yep, cool. So that is the full conditional. Again, it's proportional to the posterior, but I can drop any factors not involving mu because I'm assuming that all of those are constant, right? And that would be the full conditional for the precision for lambda. Okay? Oh, sorry, I'm missing a term there. Sorry about that. I believe that is correct. Okay. So I am regarding each of these full conditionals as a function of the parameter that I'm interested in, and all the rest is deemed as constant, right? And now, if I want to set up a Gibbs sampler, I would like to try and identify these as known distributions, right? This is a Gaussian with parameters m prime and p prime. And this is a gamma with parameters a prime and b prime. Okay? Notice that the parameters of the full conditionals are obviously functions of the data, but functions, or can be functions, of the other parameter as well, right? That's what it is mean by full conditionals. We're conditioning on the current value of the other parameters. Okay? Would it be? Okay. Are we all there? No, not yet? Not even close. Fair enough. Sorry. So now we have full conditionals, and these full conditionals can be identified as known distributions, right? So I can sample directly from them, and if I put them back in the metropolis ratios, I know that the acceptance rate will be 1, right? So the only thing that I need to do now is to start up my sampler, my Markov chain, at some arbitrary points, mu naught and lambda naught, and then update one parameter at a time, conditional on the previous one. Okay? So hopefully I have, yeah. An algorithm for that. So full conditionals for mu is a normal with parameter m prime that depends on the prior parameters and lambda and the data, p prime that depends on the prior parameters and lambda, and a similar thing but with a gamma for lambda. Okay? So I define my starting points. Mu can be any real value. Lambda has to be a positive number. And then I will update one parameter at a time, conditional on the values of the other things that I'm holding fixed. So if I start by updating lambda, I will update lambda from this gamma distribution. Sorry, I'm using stars there, primes here, but hopefully that won't be a problem. With parameters a prime, a star, these will be constant. These won't change at any point. But then b is a function of mu, so I need to use the most up-to-date value of mu, which is mu0, right? So that is the parameter that I will use. And I will accept that value with probability 1. So that will be recorded in my Markov chain. Now I will update mu, okay? Mu will come from this Gaussian distribution. You have it there. But now the parameters both depend on lambda, right? And I have already updated lambda. So I need to use that most up-to-date value of the other parameters. So P will be n times lambda 1 because I updated 1. M will be this function with lambda updated and P updated. And then that finishes the first cycle of the MCMC. I've gone through all the parameters in my vector, mu and lambda. Now, next step, I start again and update lambda. The new value will come from the same distribution, but now I have updated mu, so I need to use that value, accept with probability 1, go back to mu, use the most up-to-date value, accept with probability 1, and keep on sampling that way. So you can see the conditional distributions will be moving according to the values of the other parameters. And that's how they are updated, and that is how the autocorrelations or the correlations between parameters are transmitted into the sampler. Okay? Does that make sense? Are there any questions? Okay. There is, if you go to the web page, and we will do that on Tuesday, there's a code for doing that, and hopefully that will make understanding what is going on a bit easier. Well, the last thing that I wanted to say today is that, well, this is an example with a parameter of dimension 2. But this works for parameters of any dimension as long as we can identify the full conditionals as known distributions, right? And it works in exactly the same way. We take the vector of parameters and update one at a time by using the full conditionals. And the full conditionals are found by just looking at the joint posterior as a function of each parameter at a time. Okay? So we can drop any factors not involving that parameter, and then when we have the kernel of that full conditional, we might need to rearrange the terms so it looks like a known distribution. If we manage to do that, then we can set up a Metropolis-Hastings algorithm. Okay? Sorry. Seems awful, doesn't it? It's very nice, believe me, it's very nice. It's very useful. Hopefully, just hopefully, next week when we do some more tangible examples, how to derive each full conditional and how to work with the samplers will be a bit more clear. But well, I'll leave it there for the time being. And remember that we have next Tuesday practicals as well, okay?